Thank you, Subhojoy, and thank you to the organizers for inviting me and to have this opportunity to give you a few lectures on hyperbolic geometry. Does everyone hear me? Is this okay up there? All the way up there? Okay. So I'm not going to talk about anything new in these two lectures. In the second lecture, I'll talk a little bit about, at the end, or in the middle of the end of the second lecture, about a paper that was finished and appeared in 2022 with two colleagues, Dragomir Saric and Hrant Hakobyan. But today is going to be all mostly old stuff, and the idea is to get you to the point of just getting a taste of the kinds of things someone in hyperbolic geometry could possibly work on: topology, geometry, geometric group theory. So you all know that, well, you probably know that hyperbolic geometry, one of the big things about hyperbolic geometry is that there's exponential growth, right? There's exponential growth. So that's how these lectures are going to go. It's going to start out slowly, and then I'm going to exponentially speed up. And toward the end of the second lecture, we're going to be way out there. Okay, so I want to start with three questions, okay? And this is about the geodesic flow. So you could say this in a much more abstract way. So let me just say it in a much more abstract way. Suppose we have a smooth Riemannian manifold M, and you have the, I actually want the unit tangent vectors on M. And the geometry on M induces a flow on the unit tangent bundle called the geodesic flow. And what is it? Well, if you start with a vector, a tangent vector, on the manifold, based at some point, it points in a direction, it determines a geodesic, and you flow along that geodesic for time t, where this t is this parameter t here, and then there's a unique geodesic here, a unique vector here, which is tangent to the geodesic, and that's the image under the geodesic flow. So you get a flow on this, on the unit tangent bundle, and this sets up what is a dynamical system in this case, okay? So there's three basic questions you can ask about a dynamical system, at least a continuous dynamical system. What are the closed orbits? Okay, that's the first question. What are the orbit lengths? Okay, and the closed orbit length, this should read. And what's the long-term behavior of an orbit of a tangent vector? What happens after a long, long time? So let me just write these here. So the first was orbit lengths. Closed orbits. The second question is orbit length, about orbit lengths. And the third was long-term behavior. Okay, well, let's look at the constant curvature surfaces and just talk Turkey. On a sphere, constant curvature, positive constant curvature, say +1, you take a model for it as the unit sphere in the Euclidean 3 space. And well, if you follow a tangent vector along, you just close up on yourself, you get a closed geodesic. And in fact, all the orbits are closed, and you know exactly their length, whatever it is around this around the sphere along a great circle. So orbits are great circles. Orbit lengths are what is it? 2 pi r, 2 pi, and In some sense, there's uncountably many of them if you don't think about homotopy. Okay, so that's positive curvature. Flat geometry, curvature 0. Well, the isometry group is made up of flat plane translation, Euclidean translations and rotations, Euclidean rotations. So one thing you could construct is a cylinder, a flat cylinder, by taking a translation and identifying these sides, and you take this strip, and you get a flat cylinder here. And what are the what's happening with the dynamics, the geodesic flow? Well, if I pick a vector, I move along here, and you can see this up in the universal cover by tracing what's happening to a line. And what's happening here? Well, if I point in the vertical direction, I get a closed orbit, okay? If I point in any other direction, what's going to happen? I'm going to either go this way or out this way. So what are the closed orbits? Well, they're exactly homotopic to this one, say, okay? And you can compute the length. It's A, it's this length. So that's on a flat cylinder. There's also a flat torus, okay? So this is the next example. So that's fundamental group is generated by Z2. So you could think of that as you've taken a parallelogram and identified the two sides. In this case, I call this side, this identification F, this identification G, and it would have this form if you normalized, okay? And a typical element looks like this. It's Z gets mapped to Z plus, and this is the translation part, okay? Well, so every element here is a Euclidean translation in this group, and every element keeps invariant. Here's the picture. This parallel family of red lines. So if n plus m tau is one of the translates, then you draw the line through the origin and through that point, and when you look at the quotient of that, you get a simple closed geodesic in the quotient. So what's the orbit of a vector down here? Well, if you pick a rational direction, okay, which you could see up here, then you'll get a closed orbit, and you could compute the length. The length is this amount, n plus m tau. And so what the collection of orbits, closed orbits are these rational directions, and they have length this much. So this is the sometimes it's called a length spectrum. Notice that all closed geodesics, I'm saying the word closed geodesic, but it's the same thing as saying closed orbit under the dynamics of the geodesic flow. In the flat torus case, and in the flat cylinder case, they're simple. Those geodesics are simple. So, boy, looks like we've run out of everything to do. So we've taken care of questions 1 and 2 already in these two constant curvature cases, and really question 3 too, because you could address the long-term behavior. So what's left is negative curvature. So that's what I want to talk about now. But negative curvature, hyperbolic geometry, is intimately related with complex analysis. So I'm going to start with Riemann surfaces. So a Riemann surface is a surface that has an atlas of charts, and the charts have transition maps that are biholomorphic. Okay, so the picture looks something like this. If you have two charts that overlap, and you have coordinates z over here and w over here, then the transition, if you go from here to here, should be a biholomorphic map. Okay, and that gives you what's called the Riemann surface. And back in the early part of the 1900s, the Kerber uniformization theorem was proven. And what does it say? It classifies all simply connected Riemann surfaces. So they're either the Riemann sphere, the complex plane, or the unit disk. Okay? So notice that these two are homeomorphic, but they're not conformally equivalent. Okay? And this one's compact, so it's different anyway. Okay, so using this, you could talk about Riemann surfaces in the following way. So suppose we start with a Riemann surface X, okay? Well, X via covering space theory can be thought of as the universal cover. Actually, it's the holomorphic universal cover of this Riemann surface, modded out by a group, okay? Let's call that group gamma. And gamma is some, you don't want fixed points, so you take out torsion, so you want gamma to be torsion-free, and it's a discrete subgroup of the biholomorphic mappings of the universal cover, okay? And gamma acts properly discontinuously on that universal cover. So studying Riemann surfaces is the same thing as studying these gammas, these torsion-free discrete subgroups acting, well, torsion-free discrete is already implying properly discrete is already implying properly discontinuous. Actually, they're equivalent in this case. And so studying Riemann surfaces is the same as studying these groups, okay? So that's one thing to emphasize to the students. Again, I'll say the torsion-free is here to avoid any fixed points in the universal cover because you want a covering map here. And because of the action on a subspace of Euclidean space, for instance, or the Riemann sphere, gamma is countable, okay? So automatically the group gamma is a countable group. Okay, so let me back up. So if we want to study the universal cover and groups acting on it, right, we better study, well, we said that there's 3 possible universal covers, okay? And what we better do is study the biholomorphic self-maps of each one of these universal covers if we're going to try to understand the discrete subgroups, okay? So that's this next discussion. So what are the biholomorphic maps of the Riemann sphere? They're exactly the Mobius transformations. The biholomorphic maps of the complex plane are of this form. They're Z gets mapped to AZ plus B. A and B are complex numbers. A is not 0. And then the biholomorphic maps of the unit disk have this form. They're Mobius transformations, again, of this special form, AZ plus B, B bar Z plus A bar, with this determinant condition, okay? And you can prove this. You usually see this in a first-year complex analysis course. So the thing is, if we want to study the Riemann surfaces, well, the Riemann sphere is out because it only covers itself. Because if you took any subgroup of the biholomorphic mappings of the Riemann surface, they're Mobius transformations, and any Mobius transformation has a fixed point in here. So there's no way this could cover anything else but itself. And then the complex plane only covers itself, a punctured disk, or a torus, okay? So that means that all others are covered by the unit disk, okay? So the unit disk is prominent in this discussion. So we might as well, so these are understood, and then the question is to understand the Riemann surfaces that are covered by the unit disk. So that's what I'm saying over here. So here's the unit disk, and the unit disk happens to have a hyperbolic geometry. So an area element, the area element of the unit disk looks like this, okay, where Z is equal to X plus IY. Or in the upper half plane model, you could, it looks like this. Sorry, this is the area element. This is the line element, okay? And here's the line element in the upper half plane. The geodesics look like arcs of circles perpendicular to the boundary, or diameters in the disk case. And in the upper half plane case, there are again arcs of circles perpendicular to the boundary and vertical lines. And the area element here in the upper half plane looks like this, okay? And then the beautiful fact is that these are really the same thing. The biholomorphic maps of the unit disk are exactly the orientation preserving isometries of the unit disk with respect to the hyperbolic metric. Okay, so that's a consequence of the Schwarz lemma. And because of that, there's this interplay, strong interplay between the complex analysis and the geometry. Or similarly, equivalently, you could say the biomorphic maps of the upper half plane are the same as the orientation preserving isometries of the upper half plane. So when a Riemann surface has Euler characteristic, negative Euler characteristic as a complex manifold, so as a complex manifold, it's a hyperbolic surface. And I'll use the word Riemann surface and hyperbolic surface interchangeably in the next 2 days. It's necessarily interchangeable because I'm going to be flipping back and forth between making complex analytic calculations, especially in the second lecture, and geometric calculations. That's sort of part of the point of this lecture series, is to show you how you can have some very interesting questions that take you back and forth between these two areas. Okay, so by the way, you're going to see a lot of blank space. So when I wrote these notes, I, as usual, didn't pay attention to the cutoffs. So then I went back and I had to rearrange things. So there's nothing missing here. It's just blank. So the hyperbolic plane, I'm just going to denote by H. So here's an example of a hyperbolic surface, an elementary one. If you take the group generated by Z gets mapped to e to the LZ, L is some fixed positive number, okay? And you look at it acting on the upper half plane. This is an isometry group, okay? It's called a hyperbolic element. It keeps invariant this geodesic. In fact, that's the unique geodesic it keeps invariant. It's called the axis of the hyperbolic element. And it has a fundamental domain. Well, what does it do? It takes this geodesic perpendicular to this axis to this geodesic. This distance is hyperbolic distance L, okay? And in the quotient, you get topologically a cylinder, but more importantly, you get a geometry that looks like this. It flares out at the two ends, and it has a unique geodesic in the middle, closed geodesic of length L, okay? So this is important because when we start talking about hyperbolic surfaces in more generally, we'll experience funnels. And a funnel is, you cut this piece out, say, and look over here, that's a funnel. Here's another example of an elementary hyperbolic surface. Take the group generated by Z gets mapped to Z plus 1, acting on the upper half plane. Again, here's a fundamental domain for the action. This, notice, does not have an invariant geodesic. This element does not keep invariant any geodesic in here. Nevertheless, when you look at the quotient, you get, again, topologically a cylinder, but more importantly, the geometry now is very different than the previous geometry. Instead of having a funnel over here, you have a cusp. Okay, this has finite area. This comes from, say, take height 1 above height 1, and you quotient by this group, and you'll get this piece here. And that's what I'll typically call a cusp. So, yeah, so this was what I was saying before. So the Euler characteristic we'll assume from now on is negative. And when it's negative, the surface admits a constant negative curvature metric, Riemannian metric. Okay, so for closed surfaces, it's a consequence of the Gauss-Bonnet theorem, plus a construction I'm going to show you below, that genus 0 has exactly one constant curvature metric. It's the positive curvature, constant positive curvature metric, and that's it. It doesn't have 0 or minus. And the same here for genus 1. It has flat geometry and no other. And then above genus 1, you have, this is what I'm going to show you in a little while, constant negative curvature and no other of the constant curvatures. Okay. So the Gauss-Bonnet theorem, why did I say in a construction below? Gauss-Bonnet theorem says that if your say, flat geometry, then you have to be genus 1. But it doesn't construct it for you. You still have to construct the metric. Same here in genus 2, Gauss-Bonnet theorem says if you want a constant curvature metric, it has to be -1, but it doesn't say that one exists. So that's why I'm going to tell you a little bit now of a construction. And this construction is very hands-on. And the reason why I like this is because it gives you a flavor of the way, one way people look at hyperbolic surfaces. So I'm going to construct a hyperbolic metric, a hyperbolic surface of genus 2. And we're going to use right-angled hexagons. Okay, so here's a fact. Given 3 positive numbers, there exists a unique right-angled hexagon in the hyperbolic plane. Okay, so why? Well, here's an argument. Here's a picture argument why. If you start with an ideal hexagon, the vertices are at infinity, and then you start carefully bringing it in, okay, just shrinking it. If you get very, very small, you start to approach a Euclidean hexagon. Okay, and a Euclidean hexagon has angles. What is it? 2 pi over 3. 2 pi over 3. Euclidean hexagon has angles 2 pi over 3. Thank you. I'll point the laser pointer at you. The Euclidean hexagon has angles 2 pi over 3, and that's when you get very close. Shrink this to something almost non-existent, and then out here the angle is 0. So, and this angle is changing continuously. So somewhere in there, there's going to be an angle pi over 2, and there's your argument for why there exists a right-angled hexagon. And this is a stronger statement. Given any 3 numbers, they could be the alternating sides of a right-angled hexagon. Okay? So what can you do with a right-angled hexagon? Well, you have no idea. Let's see. You could glue 2 of them together. So if you take 2 isometric copies of that hexagon we just had up there, alternating sides are A, B, C, and you glue along not those alternating sides, but the seams, the other seams, these seams, this seam, and this seam, what you'll see is a pair of pants. Okay? And the pair of pants has geodesic boundary. And the boundary length is, well, this side was A and this side was A, so the boundary length is twice A, and same here, twice B, and same here, twice C. Okay, so here's an argument for given any pair of pants and any 3 positive numbers, you can find a pair of pants with those lengths as their boundary. Oh, but wait, you could do more. You could take 2 pairs of pants and glue them together. Well, look at this. Here's 1 pair of pants with sides A, B, B. And I want to glue this pair of pants to this pair of pants. So this side had better be the same length as this side. And I want to glue this side, this boundary to this boundary, so it better be the same length. So if I do that, if this is A, B, and B, and this is A, B prime, and B prime, then what I get here is a surface of genus 2. With closed geodesics, I can say exactly what they are in terms of the A, B, and B prime. I just constructed for you a hyperbolic surface. So they exist in genus 2. In fact, I constructed a lot of them for you. So you could use this to show that there's infinitely many hyperbolic structures on a genus 2 surface. So why doesn't this off the bat tell you by changing A, B, and B prime that they're different? Well, there could be an isometry between them that takes those curves to some other set of curves, and the A, B, and B prime change. But you could still use this to prove there's infinitely many up to isometry. By just, for instance, there's a Collar lemma argument. By letting A get very small, it's not going to move, it's not going to be equivalent to anything else, isometrically equivalent to anything else on the surface. So anyway, this statement is, there's infinitely many hyperbolic structures on the genus 2 surface. And this is very important, right? So this is the whole, the title of this conference is, what is the title? New Trends in Teichmüller Theory, right? So this is the whole start of Teichmüller theory, this set of hyperbolic structures or Riemann surface structures on a fixed topological object, sort of. So in general, if you have X, a hyperbolic surface, and you write it as H mod gamma, let's take away the simple examples where this gamma, which is identified with pi 1 of X, take away the ones that are abelian. So I don't want to assume abelian. Then in every free homotopy class, there's an essential closed curve, unique one. Yeah, so there's a little bit of an exception if you have a, well, okay, so what does essential mean? That's what I meant to say. Essential means you have some homotopy class, and the homotopy class, the curve in the homotopy class can't be shrunk to a point, or it can't be deformed out of cusp. Okay? So that's what essential means, and so if it's essential, there's a unique geodesic in its homotopy. And that comes from the fact that back in this picture here of this elementary example of a hyperbolic element, the hyperbolic element had a unique invariant axis, a geodesic. It's those geodesics that go down to the surface as closed geodesics. Okay, so that's how you get that if you had some curve down here in the surface, not this one, but a more complicated one, you could lift it upstairs. It's going to be in the same homotopy class as the lift that gives you this hyperbolic element, and then you could straighten it to a geodesic. Okay, so what's the conclusion for constant negative curvature now regarding questions 1 and questions 2? So we found that there's countably many closed orbits under the geodesic flow, okay? So that's question 1. And their orbit lengths correspond to lengths of geodesics. So that's question 2. So in some sense, we've answered questions 1 and 2. In this very naive way, we've answered questions 1 and 2. But question 3, oh boy. Long-term behavior. So I'm going to tell you about that. This is back to that same picture. So let me talk again. So suppose now we start with a geodesically complete hyperbolic surface. Okay. Again, we have the geodesic flow, as we were saying before, on the hyperbolic surface. Now it's on a hyperbolic surface. Earlier, I was more generally talking about a Riemannian manifold. Same definitions. And there's a measure, a natural measure that goes on this volume measure that goes on this, the unit tangent bundle, and it's called the Liouville measure, and it has this form. Okay, infinitesimally, it's dA, which is the area measure on X, coupled with the angle measure. So what does that mean? Well, if you're standing at a point, and you have some infinitesimal area that's coming from X, that's this part, and then you have to have a direction or a set of directions, and that's this part, okay? So that's what's called the Liouville measure. Every hyperbolic surface, actually, every Riemannian manifold has one. And most importantly, the geodesic flow on the unit tangent bundle is measure preserving with respect to this measure. Okay? So if you have some measurable set of vectors in the unit tangent bundle and you move them under the geodesic flow, that new set of vectors you get has the same measure as the old set you had. So once you have something that's measure preserving, you could ask lots of questions about it. And one basic question is, how random is the behavior of a geodesic on that surface? So that could be measured in different ways. One way is ergodicity. So the geodesic flow is said to be ergodic on the unit tangent bundle if the only invariant sets are sets of measure 0, or maybe the complement has measure 0. Okay, so it's full. You can't, there isn't some patch of invariant vectors which is non-zero, okay, under the geodesic flow. So this is a very pictorial, I mean, this is, there's a picture that comes with this. You could think when you have ergodicity, you have dense orbits, okay? That's a good way to visualize what's going on. And let's just look at the two possible types. So if you have a finite topological type hyperbolic surface, okay, there's two possibilities for a finite topological type hyperbolic surface. Either it has finite area or it has infinite area. If it has finite area, it either looks like it's a closed surface, or it's a surface with just cusps, okay? In either case, the geodesic flow is known to be ergodic, okay? And you can see in the picture why, right? Certainly on the closed surface, you ain't gonna go anywhere if you go, if you're going in a direction. There's no escape routes. Okay, that's not a proof, that's far from a proof, and it's not quite true, what I'm saying, but still, it's a good way to think about this. There's no escape routes. Here, you might say, wait a second, there is an escape route. I can go out this way. But wait. On a hyperbolic surface with a cusp, if you try going out that cusp, the only way you could get all the way out is by going straight out. Any little deviation will have you twirl around the cusp and then turn around and come back. Okay? You could see that back in this model. Where is it? Here. No, not here. Yeah, here. Whoops. You can see that in this model because a cusp corresponds to a parabolic element. And if you had a geodesic going in here, that's like a geodesic up here going up into this higher area of the hyperbolic plane. But if it doesn't go up vertically, eventually it turns around and leaves that area. So that's what's happening over here. If you don't go straight out, corresponding to going this way, if you go at any angle, you're going to twirl a bunch of times, which can be made precise, by the way, and then twirl back that same number of times and leave. Okay, so again, that's not a proof, but it's the right idea that the geodesic flow on here is ergodic also. So that's one type of finite topological type. So by finite topological type, I mean the fundamental group is finitely generated. Okay. The other possibility is that you have a finite topological type surface and it has infinite area. That means it has a funnel, at least one funnel. Okay, it looks like this, say. Well, now this escape route analogy really does work. You could see there's lots and lots of escape routes. So you could imagine you could write down, in fact, you could write down a set of subset of the unit tangent bundle, set of vectors that are kept invariant under the geodesic flow, and they have positive measure. Okay? Too many escape routes to, in some sense, have density of the orbit. So that takes care of finite type surfaces, finite topological type surfaces. So the only thing left is what happens if a surface has infinite type? Well, lots of things can happen. And so the rest of today And the next lecture will be about infinite type surfaces. Okay? So here's a short primer on topology and geometry, and then we'll come back to this question about the ergodicity of the geodesic flow. So we're going to deviate a little bit and just talk about infinite type surfaces. When I spoke to Krishnendu about giving these lectures, he said that one of the things that maybe some of the students haven't been exposed to are infinite type surfaces. So he emphasized that maybe that would be good. So I don't know if he's here now, but anyway, so I heeded the warning, the advice. So here we go. So here's a short primer. So infinite topological type surface means infinitely generated fundamental group. Okay. So if you compare, there's countably many finite topological type surfaces. Because the genus, by the way, all surfaces for this discussion today are orientable, and for the lecture too are orientable. So the genus, right, and the number of holes tells you exactly the topological type of a finite surface. So that's countable. There's countably many of those. We're going to see that there's uncountably many infinite type surfaces. So it's much more exotic, this world. Okay? You might not like it, but it's much more exotic. So here's some topologically infinite type surfaces. There's the Loch Ness Monster. Okay. It's also over here. There's a ladder surface, goes out infinitely far on both ends. There's a Cantor tree surface, okay? And here's a flute surface. It's a flute because it has these holes that you can blow into this part. Okay? Put your fingers on this. You need a lot of fingers. Okay. So yeah, back up. So let me tell you, so we're just focused on the topology of infinite type surfaces now, and then I'll talk about geometry. So to classify these, well, the thing to do is to look at the space of ends. Okay, so that's what this next discussion is about. So here's one way to get to ends. And before I even say that, let's just look at these pictures for a moment. So an end should be an escape route from this space. Okay? So in some sense, this one, if I go out this way, that's an escape route. If I go up here, that's an escape route. If I go over here, that's an escape route. So whereas over here on the Loch Ness Monster, if I'm going to escape, I just have this way to go. Here, if I'm going to escape, I have this way or this way. Okay, so if you want to make that precise, here's one way to make that precise. So we're starting with some oriented topological surface, infinite type. Take a compact exhaustion of the surface, call that Sn. Okay? And an end is going to be a collection of open sets where you take the compact Sn and you take take the complement of it in S. Now, the complement may have lots and lots of connected components. Choose one, that's UN. And then an end is going to be a sequence of these, okay? So you start with U1, you have U2, and they're nested. And so, for example, here's an example. This is the Loch Ness Monster. So the compact exhaustion, let's have this be S1, and then this one is S2, and then so on. Up to here is S3, and so on. Now in this case, if you take Sn, and you take S, this is S, and you take away Sn, you have this open set, okay? There's only one connected component, and then they're going to be naturally nested. There's only one connected component, and therefore, there's one end here. Okay, so that's one example. Let's look at this, the Cantor tree. So we can talk about a compact exhaustion by going like this. Maybe that's S1 up to this level, and then this is S2 down to this level, and so on. Okay, and if you go down to, even look at level 1, S1, if you take S minus S1, you have a lot of connected components. So you choose one. And then you go to the next, n equals 2, and then look over there. That'll have a lot of connected components. Choose one. And then you have this nested sequence, which we're calling an end. Usually I denote it E of S. There's a topology on the space of ends. Here's a basis for it. So here's how you do it. Give you a minute to read what's up there first. So given a connected component of the complement of Sn, okay, you define un hat to be all the ends that have E in them, okay? That have all the ends that have all the ends that are contained in this open set un. Okay, un was a connected component, and now there may be a lot of ends in there, okay? And that's what we're calling un hat. And they form a basis for the topology of the space of ends. But really, maybe you don't have to think of it this way. There's sort of a natural way of thinking of this, and we'll look at these examples and compute the space of ends for all these examples in a moment. So, by the way, it's not hard to check that, back here, I chose a compact exhaustion. If I chose a different compact exhaustion, since the ends only care about what's happening way out there, it doesn't matter what compact exhaustion was chosen. So that's what the content of this remark is. Questions so far? So there's special kinds of ends, which are called non-planar ends. Okay, so what's a non-planar end? It's when this, so the end is associated to this nested sequence of UNs. If all the UNs in the nested sequence have infinite genus, then it's a non-planar end. So in other words, no matter how far out you go in the end, you see an infinite amount of genus. Okay, so this is a subspace of the space of ends. Okay, and a fact, of course, is that if you start with a surface that already has infinite genus, then the non-planar end, space of non-planar ends has to be non-empty. And let's determine the space of ends for each of these examples. Okay, so how about this one? Loch Ness Monster has one end, right? So it's just one point, and it's in the non-planar ends. Right? So it has just one non-planar end. How about this one? Say, both of them are non-planar. Both of them are non-planar. So there's two ends, and they're both non-planar. Okay. How about the flute surface? there's countably many ends. These each correspond to an end, and they converge to that special end out there. So it looks like this. Here's the special guy. And they're all non-planar. There's no genus here. I'm sorry, planar. If the coffee was stronger, I would have gotten that right. All right, and then the Cantor set, Cantor tree. So, of course, the end structure is a Cantor set. Okay, and they're all planar. Could do one more example. People like to call, you could put little flowers on this. I'm just attaching a one handle. So have I changed anything? Well, the space of ends is still the Cantor set, okay? But now everything is non-planar, okay? And you could mix and match, by the way, right? We could have gone this way with by the way, this is called the blooming Cantor tree, the blooming Cantor tree. It's blooming like a lot of the stuff on this campus. Interestingly, we could have gone sort of done this half blooming and that half not. Whatever. Questions about this? Yeah, the question was, can you make anything any space with a non-planar end? Yes, I guess that's right. Because, for example, with this, I could have added one handles going out, and then actually that would be interesting. What does this look like? So what is this? If I added one handles here, what's the space of ends? Well, space of ends is the same, right? However, what? This one's a non-planar end, right? And these are still planar. Because if you get close up there, I don't see any genus. For this? Yes. I'm only going in that direction. Yeah, I'm only going that. Yeah, so if we did it on the ladder surface, then you'd make both ends non-planar, right? Is that okay? That's supposed to be a cut. That's supposed to be a cusp over there. Not. Yeah. I should have. Yeah, because it's a flute. If it kept repeating in that direction, it's called a bi-infinite flute. You should know your language. Okay, so the reason why I'm talking about ends, non-planar ends, is that there's a classification theorem, and it's quite beautiful. This theorem goes back much further than Ian Richards, but he had I think the first real proof of this. So what this is going to say before you read it is that the genus, the non-planar end, the space of non-planar ends and the space of ends completely classify the surface. So I'll let you read for a second, then I'll talk it through. So what this says is if you start with two surfaces that have the same genus could be infinite, okay? Then they're homeomorphic if and only if there's a homeomorphism between the space of ends, which when you restrict it to the non-planar ones is also a homeomorphism. So, you know, the one direction is clear, and then the work is in the other direction.
Planar ends need to satisfy any kind of a topological condition? Like, are they always a closed set of the ends, or?
Yes, good question. So that's a very good question. So first thing to say is that the space of ends themselves are topologically a Cantor set. Sorry, they're contained in a Cantor set, okay? And then the non-planar ones are contained, as you see in the full set of ends, and the non-planar ones are closed in there. So in the end, it all comes down to studying the Cantor set, actually, and subsets of the Cantor set. Yeah.
So this, I've seen this classification before, right? I say you have a homeomorphism that restricts to a homeomorphism.
Yeah.
At the level of non-planar.
Yeah.
So there are homeomorphisms which do not.
Yeah, right.
Is that an example?
Right.
I couldn't think of the top of my head.
Yeah, maybe I can't either, but the point is that the way to think of the space of ends, it's a double space in the topology sense. So you have a space with a subspace as part of it, and then when you talk about a homeomorphism between two double spaces, then the homeomorphism must restrict to the smaller subspace. Right. Yeah, there must be, right. So yeah, I don't think I can off the top of my head. But yeah. Okay, so that's a classification of theorem for infinite type surfaces. And so this is a complete set of invariants, the genus and then this pair. And just one thing to note here is that since there's uncountably many, it's not hard to prove, there's uncountably many subsets up to homeomorphism of the Cantor set. So if you take their complement, if you take one of those subsets and take their complement, you get an infinite type surface, okay? And those two infinite type surfaces are not homeomorphic because if they were, their space of ends would have to be homeomorphic. So that tells you right away there's uncountably many subsets, uncountably many infinite type surfaces, okay? Just based on knowing there's uncountably many subsets of the Cantor set up to homeomorphism. I think the first time I saw a surface of infinite type was in Michael Spivak's book, Volume 1, Differential Geometry. I think he has some kind of picture in there of a Loch Ness monster. I liked it. An infinite genus surface, in other words, this one. Okay, so this sort of up to this, we've addressed now the topology of infinite type surfaces. So the next little bit of discussion is about the geometry of infinite type surfaces, and there's a lot to say there, and I might have to segue to the board to do that. But let's start out with this. So again, suppose we have a hyperbolic surface. It's of the form H mod gamma. Gamma is a discrete subgroup of isometries acting on the hyperbolic plane. Torsion-free, let's just assume torsion-free, because we want a surface. Then we heard earlier, yesterday, Tengrin talked about the limit set. So let me just define it again. If you have fix a base point A, and you look at its orbit under gamma, that orbit will accumulate on the boundary. I'm assuming that this is pi1 of this surface is not abelian. So that means that gamma is not abelian and it's infinite. So we will have some accumulation. And that accumulation set is what's called a limit set of the group. Okay? And that's a closed invariant set, perfect. And it's where the interesting action of the group is. And as Tengrin said yesterday, it doesn't depend on the base point. Okay? Again, that's not hard to show either. So if you have the limit set of gamma, you could form the convex hull of gamma. Of lambda. Okay, so lambda is the limit set, and you form the convex hull in here, and it might look something like this. You have these intervals of discontinuity, they're called, and they're bounded by geodesics, and there's infinitely many of these. They get smaller and smaller in the picture. This convex hull is gamma invariant, okay? So you can quotient by it, and when you quotient by it, that's what's called the convex core of the hyperbolic surface. Okay? So this is one way to define the convex core of a hyperbolic surface. It's not hard to see that the convex core has to contain all the closed geodesics. That's because if you have a closed geodesic, it lifts to an axis of a hyperbolic element. And the axis of a hyperbolic element, its endpoints are limit points. So it has to either be the boundary of the convex hull or interior to this convex hull of the limit set. So all closed geodesics are in the convex core. And in fact, the convex core is the smallest closed convex subset of X that contains all the closed geodesics. There's countably many of these. So, by the way, closed geodesics now in this context can be non-simple. And sometimes they're more interesting than the simple ones. Questions about this? Okay, so we have the convex core. And if you have a finite topological surface, let me just ask, what kind of ends can it have? Well, there's only two types of ends it could have. It could have a cusp, okay? Or it could have, oh, I should have drawn, these should be funnels that are flaring out. Okay, there's a funnel here and a funnel here. And remember, a funnel can be modeled on this picture. Where this descends to a closed geodesic, one of these two, say. And this is the funnel part in the quotient. So this is the only thing that happens for a finite type surface. You have those two possible ends, escape routes, if you like. And in this example, the convex core is you chop off the funnels. So the main point I want you to take from this is that for a finite topological type surface, if I hand you the convex core and I ask you, what do I have to add to the convex core to get the complete, geodesically complete surface? Well, for finite type surfaces, you just have to add possibly funnels if it's not a closed surface to begin with. So that's what this statement says. If X is finite type, you can make X geodesically complete by just possibly adding funnels, okay? And then you can ask the same question for infinite type. If I look at the convex core of the infinite type hyperbolic surface, what do I have to add to make it geodesically complete? Okay, so this is a theorem. If you have an infinite type surface and it's geodesically complete, you can make it geodesically complete by adding funnels and possibly half planes to the convex core. Okay, so let me draw a picture because this is the new phenomena that happens for infinite type surfaces. I said I was going to be like hyperbolic geometry and exponentially grow, but I'm actually slowing down. Maybe it's logarithmic. Oh, this is not the good one. So let's take the flute surface as an example. All right, so now let's get down to business. I was earlier talking about the topology of a flute surface, but now let's put a geometry on this flute surface. So one way to put a geometry is, these are pairs of pants, okay? This one has two cusps and one boundary geodesic, and then the rest of these have one cusp and two boundary geodesics. So I can assemble such an object by gluing pairs of pants together, right? One after the other, whoops. So let's call these lengths L1, L2, L3, L4. Whoops, do you hear me? Hear me? I'm gonna get tied up in the wire. Okay, hold on. All right. So these lengths, we're free to choose whatever lengths we want, right? And then there's one other parameter, and that's how we glue them together. That's the twisting parameter, okay? But the way I want to do it for this structure, X, I'm going to call it, is I don't want any twisting. So I want this to be glued straight on with this. So these are orthogeodesics, and I want them to line up. So this becomes a geodesic ray when I glue it together, okay? And I want to choose the lengths to grow very fast. Okay, so I don't know, so if this is P1, P2, Pn out here, so I want the length Ln to be, I don't know, let's say it's e to the n. Okay, so they're growing very fast. Now, if they're growing very fast, so let's just focus in on a pair of pants. On that, actually. let's focus in on Pn. I'll draw it over here. So geometrically, what that looks like is this. Let's say maybe this is dn, the distance between these two geodesics. This was ln, this is ln plus 1. So these lengths are growing very fast. That forces this distance to get very small, very fast. Okay? And in particular, if these lengths are growing fast enough, these dn's, if you add them up, will converge. I can make all this precise, but for right now, this is good enough. So these converge, and notice, since I didn't put any twists, and I just said glue them straight on, that means that this geodesic ray that's going out, when I add up these lengths, right, it's finite, so I escape in finite time. So what's really happening in the picture is that these geodesics are getting very, very large, and what you're seeing is something that looks like this. And they're approaching some limiting object, okay, which is a finite distance away. That limiting object is a simple geodesic. It's not closed anymore, but it's a simple geodesic. And these closed geodesics are accumulating on it, okay? How do you see that? One way to see that is I can take this geodesic ray, lift to the universal cover. If you lift to the universal cover, what you'll see is, you'll see the geodesic ray, and then you'll see a nested sequence of lifts of those closed geodesics, and they're converging to this geodesic here. This geodesic here necessarily is simple, and it's not closed necessarily. Can't be closed, it would violate the collar limit if you like. Okay, so why did I start to talk about this? I'm going to talk more about this tomorrow, but the point is that now suppose I wanted the convex core of this object. Okay, so the convex core of X. Well, notice in the picture up here in the universal cover, this piece right here is a half plane. It's a hyperbolic half plane. And it gets moved away by any element of the group. It has to, because these are all simple closed geodesics that are accumulating here. So this half plane gets moved away from itself. So that means that the covering map just is one-to-one on this. So this gets pushed down to the quotient H mod gamma, and so you have a half plane in there, and we had the convex core of X, and the boundary of the convex core contains this boundary of the half plane. And you have to attach this half plane to get something geodesically complete. So the full statement of the theorem is that if you start with if you have an infinite type hyperbolic surface and you look at the convex core of the hyperbolic surface, you might have to add, what's missing? Possibly funnels, just like in the finite type case, but possibly adding half planes also, like in this picture. Okay. Now the subtle point is, and I'll talk about this more tomorrow, there could possibly be more half planes that you have to attach just for that one end. So that usually blows people's minds. But in this example, it was one half plane. There's a reason for that. That was because of the way I glued it together. However, there's other ways you could glue this together in which you might have to add 7 half planes at infinity, on the boundary of the convex core to complete it geodesically. In fact, any number you like. Yeah.
So when you say other ways of doing you pick a
Well, no, so you change the parameters. So even with these links, I could have changed the twist parameters. And if you change the gluing parameters, I mean, if you change the gluing parameters, then you no longer have this nice geodesic anymore, right? It's not fitting together to give you a geodesic ray anymore. So even though these numbers are summing to something finite, it's still possible that wild things are happening out there. And this is one of the things I'll tell you about tomorrow. It's a result with Dragomir Saric, which generalized the result of Matsuzaki, in which so I'll just say it for the pair of pants, give me any sequence of lengths. I don't care how big they get. You pick your favorite growing sequence of lengths, exponential of exponential. And I could find gluing parameters on here in which there's nothing to attach out there. This is complete, the structure. The convex core is everything. I'll tell you about that tomorrow. That's it. That really is it.
Any questions?
Right. Right. So let me just draw the picture. When you have some gluing parameters that are not this one, where everything just lined up nicely. So you saw this picture here, where there's a geodesic ray, and these are all perpendicular to these. What you'll see is, you could see, I can't go there. You could choose any sequence of gluing parameters, and so it may look like this. So maybe the feet that you're talking about, maybe one of them is here, and the other one's over here, and the other one's over here, and the other one's over there. So it's not enough for the lengths of the feet to converge, right? The distance between the feet is also a factor, right? Exactly. Oh, that's what you were asking. Yes, that's right. Yeah, it is, but I'm so I'd have to think about exactly what the right statement is. But yes, there's stronger properties. There's lots of things to talk about. There's the horocyclic flow also that's related. But yes, there's stronger properties mixing. I think it's possible, but I don't know. To date, we don't have anything. Right. But I should say, I mean, we haven't gotten to this yet, right? We haven't talked about the geodesic flow on an infinite type surface. That's next time. But it's going to depend on the hyperbolic structure in a very strong way. Let me just say that. What happens for infinite type surfaces? The flow. Oh.
Are the geodesic flows on different hyperbolic structures on those infinite surfaces the same?
Oh, I see. Yeah, I don't know the answer to that. Right. I don't know. Yeah, there might be somebody that knows the answer. Yeah, sorry. Somebody had a question here, though. Yeah. Right. I'm focused on orientable, but I don't know the answer to that. Does someone know the answer about? Yeah, I don't think about non-orientable surfaces, so I don't know. What's the universal cover? What was the question? Well, so the flute, so this is okay, so you mean in this construction or you mean generally? Yeah, okay, right. So I guess it's part of the theorem to say that you do this and now you ask the question, I'm just trying to process how to answer your question. You complete this by adding these funnels or half planes, and when you do, the universal cover is the hyperbolic plane. If you just talk about this, the way we constructed it, then this has a universal cover too. It's a subspace of the hyperbolic plane, and and it depends on what happened at infinity to say what the boundary of that. It depends on the gluing parameter. You can't make a general statement by just saying what's happening to the length. It depends on the gluing parameter. I mean, that's what I'll show you the theorem that says whatever's happening to the lengths, you could choose gluing parameters so that the surface itself is complete, geodesically complete. You don't have to add any half planes at infinity. So it depends on it very heavily depends on the gluing parameter. What's the word? Home? I didn't, yeah. It's definitely a surface when you glue it. The only thing is the geometry.
Infinite type surfaces. At some point, it's related to what Mahan was saying. You must say that you must prove that it does not depend on the pair of bands decomposition which you choose.
You certainly pick a pair of, but the construction goes the other way, right? I mean, we're starting with the pants and gluing, and yes, you're right. Naturally it gives, right. Yes, many, right. And wild things, right, and I can't make a statement about that. I mean, you could always choose a pants decomposition in which the lengths are getting very large, right? But I'm saying, my statement is just for this construction and these pairs of pants about the lengths and the gluing parameter. Yeah.
The case of non-orientable surface, I think it's very interesting that it's completely open.
Okay. The geodesic flow question or the everything? Right. Who asked the question about non-orientable? Sorry. Yeah. So here's your answer. I see.
Okay, so if there are no other questions, let's thank Ara again.